Hi everybody, this is Austin Hoggett here to give you another OpenStax Intermediate Algebra lecture. Today we're going to be talking about solving radical equations. And there's two versions of this problem, one where we only have to deal with a single radical expression, and those in which we have to have two radicals in the expression. So let's get started. When we talk about solving radical equations, one thing that's important to understand is one of the introductions of a new property of equality. In the previous instances of multiplication for radicals, we said that if I had the square root of some expression multiplied by itself, what this created was a perfect square expression. We talked about how the exponent and radical are sort of opposites of one another, and therefore their operations cancel, leaving me with just the expression underneath. We'll take advantage of this fact in order to be able to solve radical equations today. In the first example, we'll follow these steps to arrive at a solution. We need to isolate any radicals by themselves on one side of the equation using our basic properties of equality, addition and subtraction. Then we can eliminate the radical by raising each expression on either side of the equation by the index. Our exponent needs to match whatever the index is so that it cancels out. Then we'll be left with one of two scenarios. Either a linear equation that can be solved as we would any kind of normal addition, subtraction, multiplication, division equation problem. And then, of course, we may end up with a quadratic, which is a little bit more complicated and requires either factoring and the application of the zero product rule, or what we'll talk about later, which is the quadratic formula to solve. We have to check that the answer we get in the algebra is actually going to give us a true statement when we plug it back into the original equation here. Because we've introduced some of this raising of both sides to some power, we may accidentally introduce some extraneous solutions into our problem. So let's take a look at the first example here. In our first example, we need to start by isolating our radical so that we can undo that operation. So the key here is to recognize that we have our radical expression and some constant on one side of the equation first off. We can move that constant to the other side by addition, leaving me with just the radical by itself. So here we have the square root of 5n minus 4 is equal to 9. Once in this format, we can undo the operation of the square root with exponentiation. If we square one side, though, we have to also square the other. This is maintaining the initial equality given by the problem. So the square root of anything squared is going to go away. We're left here with just 5n minus 4. 9 squared, of course, gives me 81. This produces a nice linear equation. What makes it linear is that the highest exponent on my variable is 1. So we can use our regular properties of equality to finish the problem. We move constants to the same side here by addition, leaving me with 5n is equal to 85. And then lastly, we divide each side by our coefficient to get our solution of n equals to 17. So before we declare victory, again, we need to ensure that the number we got here is actually going to give us a true statement back into the original problem. So when I plug in to the original equation, n equals 17, I get something like 5 times 17 minus 4 minus 9 should be equal to 0. So the product here of 5 times 17 is going to give me 85. If I subtract 4, that should give me 81. The square root of 81 is 9. And so we end up with something like 9 minus 9, which is, of course, 0. So we can, in fact, confirm that, yes, this gives me a true statement. And so it must be the case that I have a correct answer. This process of checking our algebra has not always been critical in instances where we just start with a linear equation. However, for these roots and radical problems, it's going to be critical to always check that we get a true statement back in the original problem. So let's continue with another example here. By a similar token, I want to start this problem by isolating the radical term. We can do that by moving our constant again to the other side here. In this instance, I get the square root of 10z plus 1 is equal to 2. And again, to isolate our radical is just so that we can undo that operation with the exponent. So we use a square because it matches our index for the root. The expression 10z plus 1 pops out from underneath that radical. And on the right-hand side, we get 2 squared is positive 4. Moving our constants to the same side by subtraction here, I'm left with the expression 10z is equal to 3. So what I'm left with when I'm doing the division of 10 to each side is a fraction, of course, but that is going to be what we plug back into our expression. So again, before I declare victory, I want to come back and say, okay, well, is this really going to give me a true statement if I plug it into the equation? So we plug in 3/10, and what we'll find is that the product underneath the radical is going to give me 3 plus 1, so 4. The square root of 4 is 2, and of course 2 minus 2 gives me 0. So just as before, we do actually end up with a true statement again, and we can confirm that yes, this is in fact the correct answer. So what happens if I plug it in and I get a false statement? Well, we create what's called, again, an extraneous solution, and we have to toss that particular value out. We're not always guaranteed that we're going to have extraneous solutions, and we're not always guaranteed to just have one solution. Let's look at some more examples, though. In this instance, again, I want to start by moving my constant term to the other side of the equation by subtraction. You'll notice in this instance, too, I also have a variable on both sides of my equation. And so when I move that constant to the other side, sure enough, I've isolated my variable term. I get square root of p minus 1 by itself. But on the right-hand side, I have the binomial p minus 1. Squaring each side of the equation is going to produce, in this case, a quadratic equation, which is going to be a little bit more complicated to solve. So when I take and raise each side to the second power, I have this binomial multiplication that I need to identify the solution of. On the right-hand side, I have p minus 1 squared. Your special products will make quick work of these types of problems. This is in the form a minus b squared, and so the solution is going to be a to the second minus 2 times a times b, which in this case is 1, plus b squared, which is 1 squared, so just 1. So given the sort of setup of the problem, I can arrive at my trinomial on the right-hand side fairly quickly with a use of a special product formula. My root and exponent cancel each other out on the other side, and I'm left with the following quadratic. How do we solve quadratics? We set them equal to 0, factor, and solve using the zero product property. In this case, to set the equation equal to 0 now, I need to move everything to one side of the equation. So let's subtract p and add 1 to each side. With this, we're now left with 0 on the left-hand side of the equation is equal to p squared minus 3p plus 2. In this case, we can solve by, again, applying the zero product rule after factoring. We can apply the AC method to arrive at the factors p minus 2 and p minus 1. The values negative 2 and negative 1 can multiply together to get me the constant at the end, but add together to give me negative 3 in the middle. In this case, we set each of those factors equal to 0 and solve. And so we get our two solutions here of p equals 2 and 1. We do need to confirm that these will give us true statements in the original expression. With a quick glance, we can see that, for instance, a substitution of p equals 2 would give me the square root of 1, which is 1, plus 1, which is 2. And I would very quickly see that we get a true statement like 2 is equal to 2. If we replace p with 1, we get the square root of 0, which is 0, plus 1 is equal to 1. So again, another true statement. So it turns out both of these answers are useful, which should be no surprise given that we started here with a quadratic. We should expect there to be two solutions to the quadratic, but not necessarily that they both work in the original equation. So let's take a look at another example here. In this case, it's similar in form to the last, and so again, we would start by moving our constants to the same side. Once I accomplish that goal, we get the square root of x minus 2 equals x minus 2. So once we square each side again, I have this instance where we have to find the product of binomials here, x minus 2 times itself. The left-hand side we can make quick work of, recognizing that the exponent and radicals cancel each other out. Over here we should end up with something like x squared minus 2 times x. So we will have a coefficient of negative 4x, and then of course 2 squared or plus 4. Just as before, we want to, now that we have this quadratic, set it equal to 0. So we'll move all of our terms to one side of the equation. I can accomplish this by subtracting x from each side and adding 2. So now we end up with a quadratic 0. Spoilers here, sorry. Here we go. Oh no. 0 is equal to x squared minus 5x plus 6. Again, using the AC method, I want to look for factors of 6 that will add up to negative 5. The values will be x minus 3 and x minus 2. And the zero product rule allows me to set those factors equal to 0 and solve for my two solutions. In this case, we get x equals positive 3 and x equals positive 2. Once we substitute those back into the original equation, again, we can confirm that these do in fact give us true statements and are the correct answers. Let's look at the slide that just really wanted to show up here. In this case, I have not a square root, but a cube root. There's really not much difference in this problem versus the last ones. Again, we want to start by isolating that root expression. So we can subtract our constant from each side here. To do so, we end up with cube root of 5x plus 1 is equal to negative 4. In this case, since I have a cube root, if I want to undo the operation of a cube, I don't use a square, I use an exponent of 3. So we'll raise each side to the third power in this case. When I do so, I'm left here with 5x plus 1. And on the right-hand side, we get negative 4 cubed is negative 64. If I were to move those constants to the same side by subtraction, we would end up with 64, or excuse me, minus 65, like this. Through division, we end up with our solution here, which is x equals 13. As always, confirming that this works by plugging it back into the original equation gives us some true statement like 4 is equal to 4. So yes, this is indeed a correct answer. So let's look at another example where we don't necessarily get two solutions, although it may look like we should. In this case, I have what looks similar to some other examples we've seen already. Everything seems to be on one side of the equation, however, so to isolate our radical, we'll start by moving these other two values, r and 2, to the other side. R's will cancel, 2's will cancel, and I will be left with the expression square root r plus 4 equals r minus 2. Once we've isolated our radical again, we square to get rid of it. And so we'll end up with the expression here, r plus 4 on the left-hand side of the equation. And on the right-hand side, we end up with, by distribution and multiplication, r squared minus 4r plus 4. Since we have a quadratic, we need to set it equal to 0 and solve using the zero product rule again. This will be a little bit different than before because what happens when I subtract my expressions here is that I'm left with a slightly different expression for factoring than we have previously. I'm left here with r squared minus 5r. Notice our constants cancel each other out. And so I'm still going to factor and use the zero product rule here, but what is it that these two terms have in common? If I remove the common factor of r, I am left with a single monomial term and a binomial. We can still apply the zero product rule here and say that, well, the first expression, r minus 5, must be equal to 0, or the second factor must be equal to 0. Well, immediately we get one of our solutions, which is r equals 0. However, if we plug it back into the original equation here, notice that we have something like 0 plus 4 minus 0 plus 2 equals to 0. The square root of 4 is 2, and so I actually don't end up with a true statement. I'm left with something like 4 is equal to 0. Since this is a false statement, this must be one of these extraneous solutions we mentioned before. Solving the other example here, or the other factor for the value 5, would result in the only solution for this equation. Again, if I replace my expression here with not 0 but 5, I'm left with something akin to the following expression. And in this case, again, I need to identify whether or not this is going to be a true or false statement. So if I do the proper substitutions here, I do actually end up with a true statement, but only if I plug in r equals 5. The other value gives me some bogus expression like 4 is equal to 0. So there's only one solution in this case. So again, this highlights the need to always make sure that you are substituting back into the original equation the values you get from the algebra to ensure that you've actually got a solution. Here's another example that we'll look at involving a single radical term. Again, we'll start by moving our constants to the same side. By addition here, we can move the constant 8 to the right-hand side of the equation. Notice that this expression actually has a coefficient on the radical. To fully isolate this expression would require that I actually remove that coefficient, 3. So we can do that by division here. If I divide each side by 3, I'm left with finally my radical expression and a constant on the right-hand side. Finishing the problem off using the square property, when I take and raise each side of the second power, I'm left with the following equation. 3x minus 5 is equal to 16. Moving constants to the same side here by addition gives me the following equation. 3x is equal to 21. And so finally, by division of 3 on each side, we get a solution of x equals to positive 7. Is this really a solution? When we plug it back in, again, we get some kind of substitution that looks like this. So do I really get 4 is equal to 4 from this expression? 21 minus 5 is going to give me some square root that I can find and simplify. So when we subtract, we get 16. 4 times 3 gives me 12. And so sure enough, we get a true statement like 4 is equal to 4, confirming that this is in fact a solution. Now let's move on to instances where we have not one but two radicals in the expression. The method by which we'll do these problems is very similar. We just have to identify one radical to isolate at a time and repeat the process as we continue. Here's an easy example to begin with. Again, we'll start by isolation of one of those radicals and then raise each side of the equation to the correct exponent that matches our index. So I'm asked to solve in this case cube root of 4x minus 3 equals cube root of 3x plus 2. Again, my two radicals are really already isolated from one another. They're not, at least initially, on the same side. Because of that, I can use the exponent 3 to eliminate all of the radicals in this problem. This leaves me with 4x minus 3 on the left-hand side and 3x plus 2 on the right. Shuffling around my terms using the addition and subtraction properties, I can come to a conclusion pretty quickly about the solution of this problem. We're left with x is equal to positive 5. So in this case, when we plug back in again my equation or my variable for x, we end up with something like the cube root of 4 times 5, which is 20, minus 3, and the cube root of 3 times 5, which is 15, plus 2. So either way, we get cube root of 17, which confirms that, yes, this is in fact a solution to the equation. Not always will we have radicals immediately simplified in this way, or rather isolated. And so let's look at another example where we may have a little bit more of a challenge. So I'm asked to solve in this case, and it looks like there's two radicals, one of which is already isolated. I'll take advantage of the fact that the more complicated expression, m plus 9, is already by itself, and use that to initially start my process of elimination here. So again, once we've isolated one of our expressions, we use that square property to get rid of the radical. You'll notice that in this case, because of the fact my left-hand side has a square root, I'm going to end up with an expression when I multiply here that still has a square root in it. This is in the form of a plus b squared, and so I can use my binomial sums pattern to do the product. I'll end up with a squared, and since the square root of m squared has exponents and radicals that'll cancel each other out, I'll ultimately just end up with m. We get plus 2 times the square root of m times 1, and then 1 squared. Since 1 squared is just 1, we'll leave it as such. And on the the right-hand side, we just have m plus 9. So simplifying a bit here, we have the square root of m squared is just m. My middle coefficient here, plus 2 times the square root of m, plus 1 equals to m plus 9. We have one radical left. If we can isolate it and repeat this process, we should be able to find a solution. Before we do all that, we need to isolate that term, however. So we'll subtract each of our other terms from one side of the equation to the other. By subtraction here, we're left with 2 square root of m is equal to 8. When we get to this step, we're not quite finished isolating because we could, in fact, remove that coefficient here by division. So square root of m equals 4 finally allows us to then use the square property. So the square root of m squared reduces to just our variable. We get 4 squared is 16. So again, I've got to then ensure that this gives me a true statement back in the original problem. The square root of 16 would be 4. So my left-hand side of the equation reduces to 4 plus 1, or 5. On the right-hand side, we get 16 plus 9 under the radical. The square root of 25 is 5. So sure enough, we get some kind of true statement confirming that this is a solution.